Hello Chem 212 students, and welcome to the first of this week's videos regarding Chapter 10, Radical Reactions. Radical reactions are really important for many applications including industry and others such as pharmaceuticals and more. As we can see here in the picture behind me, this is a hydrocarbon cracking tower. And what this is used for is to break larger hydrocarbons into smaller ones that are more useful to us. For example, molecules that are around 8 to 12 carbons to be used for gasoline. And so these reactions involve a radical chain mechanism, and we're going to learn about many of these types of mechanisms in this chapter. So free radicals form when bonds break homolytically. So remember, we got two ways of bonds breaking. In all of the past reactions, we've looked at heterolytic bond breakage, where both of the electrons in a bond end up on one of the atoms in the bond. The other one doesn't get any of them. In a homolytic bond cleavage, one electron or out of the two electrons in the bond, one electron goes on each of the two atoms that were involved in the bond when the bond breaks. And you can see here, to represent that, we use these fishhook arrows that you guys have started to see a few times in other chapters. You're going to see them extensively in this chapter. The double-headed arrow, this is meant to show the movement of two electrons. In this chapter, we're going to be using a lot of this single-headed arrow or fishhook arrow that will show the motion of a single electron. So you may remember when we talk about carbocations and carbanions, that when we have a carbocation, for example, the carbon here is sp2 hybridized because it has three bonds and it has no lone pairs. And so that means its shape is trigonal planar, which has a lot of consequences for the stereochemistry of reactions that are involved. For example, in a nucleophilic attack, it's equally likely that a nucleophile can attack from the top side of the carbon here or the bottom side. Conversely, for a carbanion, that has three bonds to carbon and one lone pair on the carbon. So the shape there, the geometry is trigonal pyramidal, and that makes a very different situation here in terms of the shape. And the hybridization, we have sp3 hybridized versus sp2 hybridized. When it comes to a radical is like somewhere in between. They're mostly trigonal planar, and and in terms of the way they react in the way like a carbanion, in the way a trigonal planar molecule would. And this is because although there's an electron, like they're in the unhybridized p orbital here, like they're or like there would be in the hybridized sp3 orbital for a carbanion, this location of this electron will rapidly interconvert between one side of the carbon atom and the other. And so effectively, the shape is not quite trigonal pyramidal. It's like a shallow pyramid that's rapidly interconverting between the two. So the shape effectively is like the average between these two flipping pyramids here. And so effectively, in terms of reactions, it behaves much like a trigonal planar molecule would, like a carbocation would, in terms of its shape at least. In terms of its actual reaction, they'll differ quite significantly. When it comes to the stability of radicals, it's a similar type of situation as we had for carbocations. Radicals, they have no formal charge, but they still are missing an electron, because the carbon atom does not have an octet. It only has 7 electrons around it, or whatever atom. Usually we're talking about carbon. So here, this carbon atom, it has 3 bonds, each with 2 electrons, so that's 6, plus 1 radical electron, 1 unpaired electron, and so that's a total of 7 electrons. The radical will be more stable when the electron density can be spread out. And so that's going to be the case when we have other carbon atoms that are close by. And so, somewhat like carbocations, but for different reasons, the tertiary radical will be the most stable. again, able to kind of delocalize a little bit this electron density around this carbon for this one unpaired electron. Secondary will be less stable, primary less stable than that, and a methyl radical is the least stable. In terms of the bond strength, when we think about which bond can be broken the easiest, this is also related, kind of like the way we thought about for acids. We thought, oh, a substance will be more acidic if it has a uh, more stable anion that remains, right? And we evaluated the stability of that anion based on REO. Similarly, the bond strength here depends on how stable the ultimate the ultimate radical will be. So when for example, if we're going to break this carbon-hydrogen bond here, the resulting radical would have an electron on this carbon, which is tertiary. And due to that more stable result, it's going to take less energy here to break this bond. And so we'll have less bond dissociation energy than for a secondary hydrogen on a secondary carbon here, as opposed to even greater bond dissociation energy for a hydrogen attached to a carbon that's primary. And finally, for a methyl hydrogen, the bond dissociation energy will be the greatest out of all of these. The more stable the resulting radical, the weaker the bond will be, the easier that it can break and ultimately produce that more stable radical. Also, we're going to be taking a look at the resonance that unpaired electrons can be involved in here. And so remember that we had 5 patterns for resonance when we talked about, ions, basically, when we talked about cations and anions. When it comes to radicals, we're going to have similar types of rules here. For example, an allylic radical is stabilized due to resonance. The way you draw the resonance with the arrows now, we'll use fishhook arrows, though, and we've seen a few examples of these as we've progressed through the chapter. For example, in the last chapter regarding alkynes, we saw something like this associated with the dissolved metal reduction that had sodium. Now, when we look here, this electron here is in a unhybridized p orbital, so it can move around. So are these electrons here. So we got 3 electrons in unhybridized p orbitals here. And so we can say this electron goes into making a pi bond here. One of the electrons from this double bond goes into making a pi bond here. And that's represented with these 2 arrows right here, one here and one here. And then this last electron now goes on the other carbon, and we have the other resonance structure. And like we all do for all resonance structures, we put a double arrow between them and put brackets around the complete set of resonance structures. Similarly, if we have a benzyl radical, the benzyl radicals are particularly stable as well. And this is due to massive resonance around the benzene ring. So just like we saw with the last example, to show this resonance using arrows, we take one electron using a fishhook arrow from the pi bond and put it to make the pi bond on the neighboring carbon-carbon bond. And then we put the one electron from the radical that's involved in the pi bond, and then the one remaining electron goes on the other carbon that was involved in the double bond. And then likewise, we can keep doing this all the way around the ring to get 5 different resonance structures. So this benzyl radicals are massively stabilized by resonance, similar to how a benzyl carbocation is stabilized due to resonance significantly. Resonance stabilized radicals will be more stable than the tertiary radical. Now, tertiary radicals there's a stability to them. For the carbocations, the stability was due to the hyperconjugation, which doesn't exist for these radicals. It's not the same type of stabilization. It just allows a little bit more movement of the electron. Therefore, resonance stabilization becomes even more significant for radicals, because in this case, the electron has much more freedom to move around. It is much more delocalized. And so we can see here for a, a tertiary radical that is produced, um, we can see the bond association is associated with making that tertiary radical is 381 kilojoules per mole. To make the vinyl radical here, that's going to produce a much more stable radical, and so you can see that the energy required to produce it is significantly less. And then likewise, for a benzyl radical, this is even more true. The benzyl radical is highly resonantly stabilized, so that makes breaking this carbon-hydrogen bond much easier. It makes a more stable radical, and so we can see here that the bond association for a benzyl hydrogen here is going to be only 356 kilojoules per mole. Similarly, when we talked about vinylic carbocations, we said they are particularly unstable, right? And vinylic but radicals are especially unstable. So, as we can see here, if we're breaking a CH bond on a carbon that's involved in the double bond in the so-called vinyl position, breaking that bond is going to cost a lot of energy. Just compare that to the last slide. In the 380s for the tertiary radical here production, breaking the tertiary carbon-hydrogen bond here, breaking the vinyl carbon-hydrogen bond costs a lot of energy because it produces such an unstable radical. Likewise here, you can see this is even greater than it would be for the primary carbon-hydrogen bond breaking to produce the primary radical. And the allylic, of course, due to the resonance stabilization of the resulting radical breaking the CH bond in the allylic position is much easier with a much lower bond association energy. A radical in the sp2 orbital is even less stable than one in the sp3 orbital. So, like ionic mechanisms, radical mechanisms are going to follow certain patterns. We had 4 distinct patterns that we saw in ionic reactions. If you recall, the proton transfer, the nucleophilic attack, the carbocation rearrangement, and the you can think of the 4th one right now. But like similar to that situation, we have certain patterns that were observed in terms of ionic mechanisms, but there are some differences. For radical mechanisms, you cannot have a carbocation rearrangement in the same way. So remember, this carbon is 3 bonds, no lone pairs. It's completely lacking 2 electrons. So it can go and make a bond, and that's no big deal. But radicals have this extra electron. There will not be a rearrangement to produce a more stable tertiary radical. So that's one key difference here between ionic mechanisms and radical mechanisms. Now, in ionic mechanisms, as I mentioned, we had the 4 arrow pushing patterns for ionic mechanisms that we've been using, throughout this semester. For radicals, we're going to have 6 patterns of arrow pushing mechanisms. Now, 6 sounds very intimidating, but it's not that bad because really it's going to be 2 pairs and then 2 more. So remembering the pairs isn't as hard, right, as remembering 6 individual things. So here we see the first is the breakage of the homolytic cleavage of a bond. So in homolytic cleavage, 1 electron goes on one atom, 1 electron in the bond, the other electron in the bond goes on the other atom, and we get 2 separate atoms here, each with unpaired electrons. In order to do this, you need to smack this with pretty high energy. So you can either get it really hot, so this bond kind of jiggles apart. This is called pyrolysis. That was actually the subject of my research when I got my PhD, was pyrolysis of hydrocarbons. And so you can heat them up and break the bonds homolytically, or you can smack them with UV light, which will break the bonds homolytically. That's one of the reasons why you, as a person, do not want to go outside too long in the sun, because the UV rays there begin to do homolytic cleavage on some of your bonds, which usually isn't good. That's what causes a sunburn. And so that's that high energy light. You can't be exposed for it for too long on any molecules. This ultraviolet light here is high enough in energy to break bonds. Um, Lower the next lowest energy of light, visible light. We're always surrounded, bathed in visible light. It's not a big deal. It doesn't break bonds. Even lower in energy, radio waves like 5G and stuff. These are so low in energy. There's no way they're going to be breaking any bonds. So people's concerns with their 5G, messing with their chemical bonds and giving them cancer is probably not very well founded. It does take UV light, but UV light can break bonds. We can have addition to a pi bond. And so this is similar to addition reactions that we saw in the ionic case, but instead of adding a hydrogen and an atom, we're just adding that one atom. And the atom has to be a radical to initiate the reaction. The unpaired electron in the radical goes into forming the bond. One electron in the pi bond goes into forming the bond, and then the remaining electron in the pi bond will go on the other carbon atom that does not attach itself to the new radical that reacted and added to the pi bond. The next one here is hydrogen abstraction. So note that this is different from proton transfer, right? In proton transfer, the hydrogen leaves both electrons behind and takes no electrons with it. In this case, that's not true. One electron in the radical goes into making a bond to the hydrogen. One electron in the bond between the hydrogen and the atom it's currently bonded to goes into making that bond. And then the remaining electron in that bond between the hydrogen and, let's say, the carbon right here is left there on the carbon, and that bond breaks, and we get a radical and then a bond between our former radical and the hydrogen. Another one is halogen abstraction, which works in a similar way, but instead of a hydrogen atom, you have a halogen here. And so again, the radical here produces uses its one electron, and then one electron from the bond here goes into making the new bond between the former radical and this X atom. X generally, again, this is usually representing halogen atoms. These halogens tend to have the bonds that will break a little bit more easily than the carbon-carbon bonds. And then one electron's left behind on the other atom, leaving a radical there. And so notice all of these reactions, these four, they end up producing radicals, one or more radicals, right? That's the first four. The remaining four are going to be a little bit different here. So this one, notice elimination here. So when we talked about addition and elimination, we said they're opposites, right? Addition is the opposite of elimination. Similarly, this is the case here too in radical mechanisms. So the elimination is just the opposite of the addition. Whereas before, in addition, this atom produces a bond here with this carbon, and then an electron, the unpaired electron, is left behind on this carbon. We do the exact opposite here. The unpaired electron goes into making the pi bond, remaking the pi bond. Here, one electron that forms the bond between this carbon and this, let's say, halogen atom, goes into the pi bond as well, and then this atom here, this halogen atom, leaves as a radical. Finally, this last one, coupling, this is how the radical reactions end. When two radicals, each with their unpaired electron, both give their unpaired electron to produce a bond. And so those are our 6 arrow pushing patterns, analogous to the 4 arrow pushing patterns that we had for ionic compounds, but a little bit different because we're dealing with radicals instead. So as I said, we can kind of picture this here as kind of pairs of reactions. These 6 patterns can be kind of condensed into 3 pairs. I said 2 pairs and 2 reactions because I feel like hydrogen abstraction and hydrogen abstraction is actually kind of just the same thing, but it's different in this case because here hydrogen is being abstracted by a halogen atom, whereas the other way the hydrogen is being abstracted by a carbon atom. But either way, you can arrange these essentially into three pairs. So first of all, homolytic cleavage is the breaking of a bond where two atoms get a single electron here, whereas coupling is the exact opposite. The two atoms with the single electron, the two radicals, they then use each of their electrons to share them and make a bond. Um, Addition and elimination being opposites of one another. And then finally, hydrogen abstraction. Again, these are both called hydrogen abstraction here. Uh, and in this case, we have hydrogen abstraction by the halogen atom versus hydrogen abstraction by the carbon atom. And so those are the six processes arranged here. These six processes arranged into three pairs. Now, notice this is a little bit different, right? Like I said, when it comes to hydrogen abstraction, this looks like a hydrogen abstraction, but it's actually a halogen abstraction, but it's similar, right? The results are similar. So that's why I say two pairs. And your book says three pairs. I kind of say two pairs and two reactions. It's kind of like you kind of go both ways with this here. But yeah, that's just a way for you to kind of, especially with these guys right here, these are clearly opposites of one another. So that's a way to organize this into your mind. Hydrogen abstraction versus hydrogen abstraction. This is two ways. So what's not mentioned is the halogen abstraction, right? But so it's not a perfect analogy, but definitely these work very well. So I would chunk these in your mind as two things rather than six things, right? That makes things a little bit easier. Or two things, these two rather than four, I mean. Okay. So let's take a look at each of these steps individually as they occur as parts of a radical mechanism. So radical mechanisms are approached in a little bit different than ionic mechanisms. When an ionic mechanism usually starts, when an ion is made, and usually at the end there's no ion anymore, right? There are ion intermediates, but you end up with a stable product without a charge, right? Analogously, for radical mechanisms, they have certain parts to them. First, but those parts are very standardized. First will always be the initiation. The initiation is where a radical is formed. So this will generally be by a homolytic bond cleavage, will produce two radicals. Then there's propagation, which is the next step. Those involves the steps where radicals produce other radicals, right? And finally, termination involves the coupling of radicals to produce a stable compound that is not a radical. So the initiation step is where radical species are formed. That's due to the homolytic bond cleavage, produces two radicals. When it comes to propagation, propagation steps can take many forms, but all of them involve starting with a radical and producing another radical. So this will occur when you have the addition to a pi bond here, starting with this radical, ultimately producing a radical. It will occur when you have a hydrogen abstraction. Again, starting with the halogen radical here, producing a bond between the halogen and the hydrogen, and then ultimately producing a hydrocarbon radical. Halogen abstraction, again, same thing, except abstracting a halogen atom, so you get the bond between here. This is a hydrocarbon radical. You get a bond between the carbon and the halogen here, and then you have a halogen radical. And finally, elimination. In elimination, you get this double bond. However, you still have a radical produced from the leaving atom, which is often a halogen atom. Finally, termination steps always involve coupling. So these are what get rid of the radicals. When two radical species come together and produce a bond, then you no longer have a radical. And so when we discuss the mechanisms, they're not going to be a straight line, though, like they are when we talk about ionic mechanisms, where first this happens and then this happens. Along the way, you're just going to produce a bunch of different radicals, and eventually some of those radicals will find one another and couple, and then the reaction will slow down. But because there's so many ways for propagation to occur, radical mechanisms tend to be kind of wild and crazy. They're out of control. Think of burning something, right? That combustion, that's a radical chain mechanism, and they call it radical chain mechanism. It's going to keep on going, unless in some fashion these radicals are quenched, meaning they react and couple in order to produce a molecule that is not a radical anymore and won't be as reactive. So let's talk about now how we produce a halogenated compound. So you may have noticed we've done some stuff in the lab with halogenated compounds. And you might have noticed we were very careful. We didn't use very much of them. It's because it's actually quite challenging to make a alkyl halide. And the reason why is because you have to use a radical chain mechanism. And as I've expressed, radical chain mechanisms are a little out of control. They're hard to stop once they get started. Radicals really want to react, and a lot of times when they react, they produce more radicals. Um, and so the general process that we're going to be using is we'll take a hydrocarbon, like in this case methane here, we'll react it with a halogen in the presence of light, and the light is going to be used to break the bond between the halogen atoms and produce radicals as an initiation step. And then there will be propagation steps in which the hydrogen here is abstracted and the chlorine is replacing it, or the halogen atom is replacing it. So here are and this is going to be very important because when we were doing reactions in chapter 7, all the interesting substitution and elimination reactions we did, they all started with alkyl halides. However, alkyl halides generally aren't what we find, we dig out of the ground. What we dig out of the ground here is hydrocarbons a lot of the times, or we use these to produce the alkyl halides. And so we need to have a way to produce these, and this is that way. So it starts with a homolytic bond cleavage where we expose halogen molecules to a UV light, and then they do a homolytic cleavage producing 2 halogen atom radicals with unpaired electrons. The next step here, so that was initiation. That produces the radicals. Next is propagation, and all of these steps produce more radicals, right? So one of the propagation steps is going to be the abstraction of hydrogen by the chlorine atom here. And so this bond breaks. 1 electron from the bond goes to making the bond between hydrogen and chlorine. 1 electron from the chlorine goes into making the bond between hydrogen and chlorine. And then 1 electron is left behind on the methyl. And so we have a methyl radical now. Now that methyl radical can go on and react. It can do a halogen abstraction. We still have chlorine molecules here. And so this unpaired electron on the methyl can go and be involved in a bond with a chlorine if 1 electron between the chlorine and the chlorine goes into making this bond. And then finally, the other electron in the bond between the chlorine and chlorine is left behind, and we get another chlorine radical here. And now we have the methyl chloride produced, chloromethane, to use the systematic nomenclature. And we have another chlorine atom. So in both of these cases, these are propagation steps because they continue to produce radicals. Finally, we're going to have the termination steps, and this is when any radicals combine and to create a bond and thus eliminate the radicals, or remove them. They're no longer there is what I mean, not as in elimination, but they're no longer there. So this can occur when 2 chlorine atoms couple. Each of their unpaired electrons goes into making a bond, and we get our chlorine back. We can have a coupling between a methyl radical and a chlorine atom, and this will produce more chloromethane. Or we can have the coupling between the 2 methyl radicals, which will produce a bond between the 2 carbons and produce a larger hydrocarbon here. And so you can see that it's not a straight line path, as I said, like we have in an ionic reaction, where we're just going to get one product, and it's very clear that, or at least, a pair of enantiomers or something, where it's very clear what product we're going to get and what ratio of products. As you can see, we've got lots of products here. We've got ethane, we've got chloromethane, we get our chlorine back, we got chloromethane produced in another way, too, during the propagation. And so, there's a lot of kind of chaos to radical mechanisms, and that makes it hard to use them synthetically. But we do use them oftentimes to halogenate alkanes. If you want to know what the overall steps in the reaction are, well, note that the initiation step and the termination step are kind of opposites of one another, right? The initiation step involved the homolytic cleavage of the chlorine bond, and then one of the termination steps involves the reforming of the chlorine, the other forming the chloromethane. So if you want to know the overall reaction process for a radical reaction, what you do is you take all of the propagation steps alone and you add them together, because the propagation steps use up radicals, produce new radicals, and so we can see here, for example, one of the propagation steps was the hydrogen abstraction, where we got a methyl radical and then we get the HCl here. The other halogen abstraction involved the methyl radical and a halogen abstraction where we ended up with a chlorine attached to the carbon here, and that produced a chlorine radical. And so these steps, they essentially produce each other's reactants, right? The halogen abstraction reproduces the chlorine atom, which then can go and react with the hydrocarbon, the methane, and produce a methyl radical, which will then get used up in the next step. And so these reactions can continue and continue and continue. As long as you keep feeding in methane and chlorine, this reaction will continue and continue and keep producing chloromethane and HCl. This is referred to as a radical chain mechanism, or a propagation chain reaction. And these chain reactions will just continue and continue and continue. And so, as I said, that makes halogen reactions a little more out of control than the ionic reactions that we've been studying before. One example of this is it's very difficult to just get chloromethane. Um, or one, it's very difficult in general to halogenate a hydrocarbon just once, because because if we have a lot of chlorine, we can add a chlorine once to the methyl chloride, but that can itself react in the radical chain mechanism, and there can be a hydrogen abstraction, then a halogen abstraction, and we can get another chlorine, and then we can add another chlorine and another chlorine. So you have to be very careful of the reaction conditions. If we have too much chlorine, then the products of our halogenation will continue to be halogenated until all of the hydrogens have been removed and replaced with halogen atoms. So it's actually significantly easier to produce just carbon tetrachloride than it is to produce just chloromethane or methyl chloride. The way that we make sure that we just produce chloromethane as opposed to carbon tetrachloride is to, or tetrachloromethane as it should be systematically called, is to have lots and lots of methane but not a lot of chlorine. So you can't keep adding it as easily. Or are we still going to get some of these? Yeah, a little bit. But by keeping the methane concentration high, we can keep that to a minimum, or that's the way they try. Again, these reactions are a little bit harder to control than ionic reactions. So in terms of doing these reactions, you notice they're always going to start with an initiation step, meaning we have to produce a radical in the first place. That means we need to have a relatively weak bond that we can somewhat easily break. And some examples of those are halogen bonds. The halogen bonds are not particularly strong, any of them. In the case of the chlorine and the fluorine, they're weak because each atom is electronegative and wants to pull that bond apart. They're both pulling on the electron. And so that really helps a homolytic cleavage step happen, because each atom wants its own electron. And so that's pretty easy to initiate with ultraviolet light or heat. Very, very low bond dissociation energy here, quite low, 243 kilojoules. Now, we've looked in the past at hydrohalogenations involving peroxides, and this led to a radical chain mechanism that produced for us a anti-Markovnikov addition with the peroxide rather. So the reason is because, just like with the chlorine and the fluorine, oxygen really pulls on electrons even harder than chlorine. And so if you have a bond between oxygen and oxygen, it's quite weak because each oxygen wants to take its own electron and go home. And so you can see that results in a very low bond dissociation energy. Likewise, we can have so-called acyl peroxides. These are peroxides in which there's also a carbon-oxygen double bond in the same carbon that is attached to the oxygen in the peroxide bond. And the result is that these produce two stable acyl radicals. These stable acyl radicals here, the fact that they're so stable means that it's easier to break this bond here. And so you can see the stability here. We'll probably see it on a subsequent slide here, but we have these fishhook arrows here, and then like this. Whoops, one-headed arrow. That's supposed to be a one-headed arrow, guys. And then we have the carbon here, oxygen. The oxygen's a radical now. Have a double bond. Oxygen. These are the two resonance structures. So the fact that this product is resonantly stabilized makes it even easier to break this bond. And so these are what are referred to as radical initiators. It's pretty easy to break the bond, and so we can use these to produce radicals. The acyl peroxide, clearly because the weakest bond is most reactive. If you have an acyl peroxide, you can initiate the reaction simply by heating it somewhat above room temperature. So these are clearly highly unstable peroxides. They'll break into radicals and start reacting very easily. Radical inhibitors. Radical inhibitors are those that when they react with radicals, they actually produce a stable molecule rather than a radical. So there's a couple of molecules that are particularly good at this. These are also what people have called antioxidants in terms of a medical sense. Antioxidants. The process of doing just the process of doing metabolism and also being outside and exposed to UV rays. These all produce some radicals in our body, and so natural antioxidant molecules are those that will react with those radicals to produce stable molecules, so that those radicals don't go and try to react with our structural materials or our DNA and alter those molecules, because altering your DNA, getting a mutation, that's the kind of thing that leads to cancer. So one example here is oxygen. So usually we draw the Lewis structure of our oxygen like this. But as we've talked about before, oxygen really loves electrons. So another way we could do this is instead of drawing this bond right here, we can get rid of this and just show it as one of the electrons each being on one oxygen. This is referred to as a diradical. And so this can react with other radicals and then produce a neutral compound. But these radical reactions, so because of this, radical reactions will go slow in the presence of oxygen because the oxygen will quench them. That's the word people often use. Will react with them to produce non-radicals. Hydroquinone here, as you can see, if a radical is produced for this, there's going to be high resonance stabilization. I'm going to show on a subsequent slide why it is that these are radical inhibitors, hydroquinone in particular. So let's say hydroquinone reacts, and there's a hydrogen abstraction here. So we do this hydrogen abstraction, so let's remember how to use our handy dandy fishhook arrows here to show this reaction. One of our 6 types, the hydrogen abstraction. So we got one fishhook arrow here, and then one fishhook arrow is going to make this bond. And then this electron will be involved in the bond too with another fishhook arrow. And so now we end up with one electron on the oxygen. That's this electron right here. And so now this has produced a radical. However, and this radical is resonantly stabilized, so it will stick around for a little while, which means that if we have another hydrogen abstraction, so here is the other hydrogen abstraction. We have one fishhook arrow is going to go into making the bond with the hydrogen. Another fishhook arrow is going to be going to making a bond with that hydrocarbon, and then an electron will be left behind here on the oxygen. So that's this electron. So now we have these 2 radical electrons, and both of these are resonantly stabilized. But we can have now we can ultimately, what we've produced here is a diradical that, like oxygen, actually isn't unstable, but it's an unstable non-radical. And the way we can see that is here we have a we have here a allylic radical, and so we can draw arrows like this here, and then one right here. So that's going to leave an electron right here. Okay, and then we have another allylic radical here. So if I draw this, I have the oxygen here, here. I got the double bond, and I've got this right here. And now I've got the radical right in here. And now this is a double bond to this oxygen. Okay. And again, here we have, and this is a resonance structure here. So I'm just kind of showing you the steps over here to get to benzoquinone. Essentially here we've got now, I'll use a blue arrow just for contrast here. We've got another allylic radical here. So we end up with double bond here. This one produces a radical here. And now our diradicals, they're in the same vicinity. So we can redraw this now. And we have this oxygen with its, still with its radical electron. And remember, we're doing resonance structures here. No single resonance structure actually represents the molecule, right? But this is just kind of going to show why there's resonance here, why there's significant radical resonance. And so now we got the double bond here, and now we have this electron. So finally, now these two electrons, this is now like the O2. It's like O2, except this is a carbon atom, but these essentially are actually in a double bond here. And then that gives us the final benzoquinone here. And so here these are all parts of the resonance here. But that's how benzoquinone is produced. And so the fact that this initial radical that's produced is highly resonantly stabilized allows it to stick around long enough for a second hydrogen abstraction to occur. And then finally we get this very stable benzoquinone molecule. And there's no more radicals. And so that's how these radical quenchers, or radical inhibitors, as they're also called, will get rid of radicals, and that's how they function in the body as well. These various antioxidant molecules, they react with radicals and get rid of them, so that those radicals do not react with your very valuable human body part molecules like your DNA. So let's talk now about whether, about the energy and the energetics of this, whether the reaction is spontaneous or not. So remember, if we want to determine if a reaction is spontaneous, what we do is we look at delta G and we consider the enthalpy terms and the entropy terms. In the halogenation reaction, so if we're doing a halogen, so the halogenation reaction we just saw, this was the overall reaction. Here we have two reactants and we have two products. So in terms of the entropy, there's not going to be a significant change in entropy here. So what we're going to say is this whole entropy term, this is going to be close to zero, the change in entropy. So we're going to say this is close to zero. What we get is that delta G is going to be proportional to the delta H. So if we have an exothermic reaction, it will likely be spontaneous. If it's endothermic, it will likely be non-spontaneous. So we need to think about whether this kind of reaction here is whether it's exothermic or endothermic. And so we can do that, remember, from way back in chapter 1. We've done this a few times. What we can do is look at what are the bonds that are broken. That's the energy you have to put in. And what are the bonds that are formed? That's the energy that comes out after the reaction is done. And then we add that all up and we decide whether energy was overall lost or whether it was absorbed. So here the bonds that are breaking are carbon-hydrogen bond, and the halogen bond that's breaking might be fluorine-fluorine bond. So here we have the case with the fluorine-fluorine bond, very weak bond, 159. Chlorine-chlorine bond's a little bit stronger, and this is because the chlorine atoms are not quite as electronegative as the fluorine atoms, so they don't pull the bond apart as hard. Then when it comes to bromine and iodine, those atoms are not as electronegative as chlorine or fluorine, so they're not pulling each other's bond apart as hard. However, they're getting pretty big, and so the bond is getting long, and the longer it is, the easier it is to break. So you can see that iodine has the weakest bonds here at 151 kilojoules per mole. Carbon-hydrogen bond here in methyl, these are all the same, 435. The carbon-halogen bond that's produced, it's going to be the strongest for the carbon-fluorine bond, and then as the electronegativities become lower and also the bond lengths become longer, more importantly. So the carbon-fluorine bond here is the shortest and the strongest. It's also the most ionic, which also contributes to a higher bond energy because the fluorine is really pulling its electrons its way, producing almost a negative ion on the fluorine and a positive ion on the carbon, so those attract very strongly. And then the energy goes down as the bonds get longer and longer. And the electronegativity of the atom gets lower and lower. And then we have the hydrogen-halogen bond, and for similar reasons, it's the HF bond is the strongest, and they get weaker as you go down. And so if we were to calculate the delta H, what we do is we add up these bonds here, bonds broken. Those are going to be positive. We put the energy in, so we add these bonds. This plus this. Bonds broken, and we subtract the bonds that are formed. This, and so if we do that for all of these, what we're going to see here is that the production of the fluoromethane here is the most exothermic. It's hugely exothermic, so it releases lots and lots of energy. This is actually not very good for the reaction because it causes the reaction to kind of go out of control. It just gets, think of it kind of like an explosion, right? So when you explode something, it gets so hot, everything just starts reacting all at once. You get even more energy released, and boom, right? So that's the case with the fluorine. You get so much energy released here. This reaction is a bit out of control, and so it's not ideal here. Now, so this one's kind of out of control. It's too exothermic. It's going to be very, very spontaneous. But it's going to be really, really out of control. The chlorine and the bromines have this happy medium here. So these are nice. They are spontaneous. They're spontaneous. And that's because they're exothermic. But they're not too spontaneous. So not too much. And then when it comes to the iodine, this one's not spontaneous. Not spontaneous. So this kind of mechanism is going to work best with chlorine and bromine, this halogenation. So that's what we're going to usually focus on. So fluorination is so exothermic, it's too violent, it's not practical. Iodination is endothermic, so it is not spontaneous. You're not going to get a lot of products. So halogenation with chlorine and bromine are the useful ones. So, as I said, both chlorination and bromination are exothermic. When we add it up, we have for the first propagation step. Here is just looking at it in terms of a different way. We're looking at each individual now propagation step. So one of the propagation steps here was the hydrogen abstraction. And in the hydrogen abstraction, this one is going to be exothermic for chlorine, but it's going to be endothermic for bromine. And the second step with the halogen abstraction is going to be exothermic for both. And overall, the net reaction is exothermic for both, as we saw. And so the first step is going to be a little bit different, though. The first step is not going to be particularly favorable for the bromine atom. And so that's something we'll be able to make use of. The fact that the chlorine reaction here is exothermic and the bromine is not. If we look at this here, the chlorination again, this is exothermic, meaning that when we do this first step, the products are going to have lower energy than the reactants. And this seems to imply here that we would have a smaller activation energy. And this is in fact true. However, for the bromination, this first step is endothermic. So by its nature, just to get up to that end of that first step, we're likely going to have a very high activation energy. So the first step will be relatively quick for the chlorination, but it will be relatively slow for the bromination. Ultimately, both of these reactions are exothermic, so you can see that the overall delta G for the reaction here is going to be negative for the chlorination, and it's also going to be negative for the bromination. But the first step is going to be slow for the bromination due to the high activation energy. The first step is going to be relatively fast for the chlorination. We say that the bromination is more selective. So often also when we're doing halogenation, when we're doing this halogenation, we can remove a hydrogen from various places here, and we can then add a chlorine atom. So there's multiple possibilities for the chlorination. For example, here we could put a chlorine in the second carbon here, or we could put it on the first. And the number of possibilities depends on the number of hydrogen atoms. So here we have 2 hydrogen atoms attached to this secondary carbon, and then we have in this propane here, but we have 6 hydrogen atoms attached to these carbons. And so this is going to start to make us think about the regioselectivity of halogenation, radical halogenation. And we're going to start with that on the next video. I'll see you then.